Dear students, let's continue our practices on Mathematical Analysis 1, and today's topic is Taylor's and Maclaurin's expansions. Today we will consider some examples on how to write in Taylor's expansion the function f of x. Okay, if a function f of x is continuous and has continuous derivatives up to the n minus first order, and on the interval AB, of course, AB, and there is finite derivative f nth order of x at each interior point of this interval AB, then Taylor's formula is the following one. So f of x, it is fa plus x minus a f prime of a plus x minus x minus a second degree over 2 factorial f of 2 double prime, so it is second order derivative of x a at the point A, we will do it, and plus the next one is f. So here we have x minus a cubed now. X minus a cubed over 3 factorial times third order derivative, the point A, and the plus, etc. And if we want to write with n minus 1, it will be f x minus a n minus first one over n minus 1 factorial, and then it is we have here f n minus first order derivative a. We said that f of x has continuous derivatives up to n minus first order, n minus 1's order, and here we have this one, and plus the last term is here plus x minus a n's power over n factorial, and the f derivative n's order, and some kind of here xc. So, and what is xc? Where xc is e plus here the remainder of this one, so e plus theta x minus e, and theta belongs to the interval 0, 1, so like this. So if I want to again the Taylor's formula, so f of x is continuous and has continuous derivatives up to n minus 1's order on the interval AB, and there is a finite derivative f n's order. So at each interior points of interval AB, then Taylor formula holds true on this interval, on the interval AB. So now, in particular, when a is 0, so here we expand our formula in the point A. If a, in particular, if a is 0, we have Maclaurin's formula. So in our case, it will be f of x. It is, if a is 0, f of x. Now just put instead of a 0, f of 0 plus, so it is now x times to f derivative of the point 0. Now we need to expand our function at the point 0, and the plus x squared over 2 factorial f second order derivative of 0 plus etc. and n minus 1s, it is x n minus 1 over n minus 1 factorial f n minus first order at the point 0 derivative. So plus, and the last term it is x n over n factorial f n of xi. So it is Maclaurin's. It is Maclaurin's expansion. This one. So, and this one, the following one, it is Taylor's expansion. Taylor's expansion. So we have two types of these expansions. So here we need to use derivative differential calculus of this function. Okay, now let's consider first example. First example, expand the polynomial f of x in positive integral powers of the binomial x minus 3. So we need to use our Taylor's expansion. Here a is 3, yeah, because on the Taylor expansion we have x minus a, and in our case a is 3. So now we have the given function f of x, and we need to expand this polynomial. Okay, firstly we need to find the derivatives of f of x. So f first derivative, it is, here we have 9x squared minus 8x plus 2. And now find the second order derivative. It is, so one more time we need to take a derivative of this function. It is 18x minus 8 just. So now the third order derivative we have, it is just 80, yeah, and we don't have any others because here after a third order derivative we have zeros, so we can write as order derivative as 0. And now so here of course n is greater than or equal 4. So let's use the Taylor expansion and write this expanded form of this function. So for this one we need to one more thing. This is the values at the point a, values of function. So here firstly let's find f3. So it is 3 times 3 cubed, just put in instead of x, minus 4 times 3 squared plus 2 times 3 minus 3. So we have here 3 times 27 minus 4 times 9 plus 6 minus 3, or so 81 plus minus 36 plus 3. So hence we have 81 plus 84 minus 36, it is 8, and so 4. 48. And now we have 48. Now we need to find f first order derivative at the point 3. So it is 9 times 3 squared minus 8 times 3 plus 2. So it is 9 times 9, it is 81 minus 27 and plus 2. So here we have 54. So 54 plus 2, it is 56. It is 56. And now the next one is so here we have f second order derivative at the point 3, and it is 80 times 3 minus 8, so it is 54 minus 8, or it is 46. And now, and the next one, f third order derivative of 3, it is just 18 because we don't have any x here. And other ones will be zeros. So now what we need to do now, just write now the form of our expansion. So we have here now x 3x, we can write our polynomial 3x cubed minus 4x squared plus 2x minus 3 as the first one. It is f, let's repeat the formula, so fa plus x minus a, f first order derivative a, plus x minus a squared over 2 factorial f second order derivative of a, plus x minus a cubed over 3 factorial times f third order derivative of a, and the plus etc. But in this case, this etc. we have 0. So because beginning from fourth order derivative, it is 0 using this one. So just this one we can write as equal now, and fa it is f3 just, yeah. So it is f3 plus x minus 3 f prime of 3 plus x minus 3 squared over 2 factorial f second order derivative of point 3 at the point 3 plus x minus 3 cubed over 3 factorial f times f third order derivative of 3. And now just put these values. So f3 it is 48 plus x minus 3 times f prime 3 it is 56 plus x minus 3 squared over 2 factorial is just 2, f second order derivative of 3 it is 46, and the plus x minus 3 cubed over 3 factorial it is 6 times f3 it is 80. So we can simplify our expansion and rewrite the last expansion of this for this polynomial. So it is 48 plus 56 x minus 3 plus, we can cancel them, and 23 x minus 3 squared and the plus 3 x minus 3 cubed. So we wrote our expansion as in positive integral powers of the binomial x minus 3. So we have answer with x minus 3. If you open this polynomial, we get the given polynomial. And now the next example, expand the function f of x e to the power of x in powers of x plus 2 to the term containing x plus 2, for example, cubed here. So now we need to expand our function, and here if we find the derivative of f of x, it is f prime of x, it is e to the power of x. So if second, it's also e to the power of x, so we can write nth degree of this function is e to the power of x. For all n here, yes. And now the next one, it is finding the value. So f and nth order derivative of the point here minus 2 we have, yeah, a is minus 2 in our case. So minus 2, it will be, so if it is minus 2, so it is 1 over, so e to the power of minus 2 or 1 over e squared. 1 over e squared. And now, if you use the Taylor's expansion, we get the next one, e to the power of x, it is 1 over e squared. If we want to write in this x plus 2 degrees, so, and plus x plus 2 times 1 over e squared plus x plus 2 second over 2 factorial times 1 over e squared plus x plus 2, here we have cubed over 3 factorial times 1 over e squared, and then we can write, we can use small o also, so we wrote a Taylor expansion with the function of f psi. So in this case we need to write till till cubic term. So here we can write like small o x plus 2 cubed. So it means the other ones, it is bigger than x plus 2 third degree. So this is the expansion of our function f of x. And now let's try to write for sine x also, f of x sine x, so up to in the power of x up to the term containing x fifth degree. So now let's write f first derivative of x, so it is cosine x. So here pay attention, a is 0, so we need to write in Maclaurin's expansion just x, yeah. So now f of x, f prime of x, it is cosine x. So here now f prime of 0, it is cosine 0, and cosine 0 is 1. And now the next one is f second degree of x. It is the second degree of x. It is here we have minus sine x, and f the value of 0 in this one, so it is 0. Now f third, it is, again, we have minus cosine x, and the value at the point 0 is minus 1. So now a fourth order of x, so it is, so beginning from fourth, we can use the room numbers. So here we have sine x, just sine x, and it is the value, the point 0, it is 0, and the fifth order, because we need to do it till fifth degree, so it is, here we have minus cosine x again, yes, so minus cosine x, and the value is minus 1. So, and sorry, here just plus x, because sine, it is plus cosine x, not minus. So here plus 1 just. And now let's try to use the Maclaurin expansion and write expansion of sine x. So here sine x, and one more thing, here you need to find f of 0, just f of 0. So it is 0, because sine 0, it is 0. And now sine x is, the first one is f0 plus x times f prime 0 plus x squared times f over 2 factorial times second order derivative 0. This is Maclaurin's expansion, plus x cubed over 3 factorial f third 0 plus x fourth over 4 factorial f fourth degree fourth order derivative 0 plus x5 over 5 factorial f5. So the higher order derivatives you can write in room or in like this in brackets, just for like 5 of 0. So now what we have, if you put the values, f0 it is 0. You can see the odd ones are 0. The first one, I mean, look here, not odd ones, even ones. So if odd ones of derivatives, the power order, first order, third order, and fifth order are not 0, and other ones are 0. So we have just odd orders of derivatives of this function. So in this case it is f0 is 0, so the first order, and it is 1, so it's just x now, plus this is 0, second one, and third one we have, the third one is minus 1, so it is minus x cubed over 3 factorial, and fourth one is also 0, and we have fifth one. So fifth one it is so in this case it is just 1, so x5 over 5. So now we have the next term is like small o x5 or x6, we can write just x5, we can write, so it means the next one it will be the higher than x5 order, I mean. So here 5 factorial, of course. So we have the following one, x minus x cubed over 3 factorial and plus x5 over 5 factorial. And the next term, yeah, in generally it will be only odd powers of this expansion, I mean. So the next one will be x minus, and you can see here the signs also change it. So plus, minus, etc. it will be. So here we have the next one is minus x7 over 7 factorial. The next one is plus x9 over 9 factorial, etc. This is for sine x. And now using Taylor's and Maclaurin's expansions, we can expand elementary functions. So we considered e to the power of x and sine x. We can write for such kind of functions, elementary functions, the ready expansion of these functions. So let's begin. Let's begin with e again. So we have a e to the power of x. E to the power of x, it is 1 plus, this is really formula for you, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. So this is for e to the power of x. Now for sine x. Sine x for trigonometric functions, let's write. So sine x we also consider it. So it is only, however, sine is odd function, so there are only odd terms. So it is x minus x cubed over 3 factorial plus x5 over 5 factorial, for example, minus x7 over 7 factorial, and we have alternate signs, minus, plus, minus, etc. And it's so on. So the next one for cosine. Cosine is even function, that's why we have only even terms here. So beginning from 1 minus x squared over 2 factorial. Now we have only even ones. Here in sines we have odd ones, in cosine we have even ones. And the plus x4 over 4 factorial minus x6 over 6 factorial plus etc. So now the next one is tangent. So tangent of x, it is x plus x cubed over 3 factorial. Tangent is sine over cosine. So, and the next one is, here we have 2x, it will be 2x5 over 15 here, and plus etc. You can use Maclaurin's expansion and just find for tangent also using derivatives. Okay, and especially cotangents also. Now we have arcsine, arccosine, arctangent, so we can find it using the Maclaurin's expansion. Now let's write for natural logarithm. So natural logarithm 1 plus x. So it is x minus x squared over 2 plus x cubed over 3 factorial. Here we have, and minus etc. So here also we need to change our signs, and here not 3 factorial, just 3 it will be, because it is natural logarithm. If it is e to the power of x, here we have factorials, and this is beginning from x. And we can use this one and write for natural logarithm for natural logarithm 1 minus x, and other ones also. So now So we have next one. For example, we can write for 1 over 1 minus x for such kind of functions. The expansion is, Maclaurin expansion is 1. It will be x the power of n in sum. If you want to write a series, it will be 1 plus x squared, x cubed, etc. So this is for 1 over 1 minus 6, and using this one we can write for in generally 1 minus x the power of alpha, for example. So let's write it is 1 minus x the power of m, or m. So if it is 1 minus x the power of m, let's write for plus, not minus. They are same. So it is, here we have the element of combinatorics, this C, and it is like this one, 1 so 1 plus the next one is mx here, and the plus m minus 1 over 2 factorial x squared, and plus etc. The nth one is m minus 1, and etc. m minus n plus 1 over n factorial times x n's power, and plus etc. Or I said we can write here small o instead of this one. So small o x the power of n. It means the other ones, it is the powers are greater than x, and here also we can write small o. So for example, for e, generally we can write the general term as xn over n factorial n plus small o xn's 1, and here we have however this is odd terms, so it is x2n minus 1 over 2n minus 1 factorial, and the small o x, now it is just, we can write here 2n, because the next one is 2n plus 1. So now it is, for cosine we have even ones, so yeah, of course here we have minus 1 the power of n minus 1 also, because the signs are changed, and in this case also we have the minus 1 the power of n x2n over 2n factorial plus small o x 2n plus 1, because the next term is 2n plus 2 here, and for natural logarithm of x here of 1 plus x, it is minus 1. So here we have minus 1 the power of n minus 1, and xn over n, just plus small o xn. In this case it is just xn, and so plus small o xn, like this. So this is the expansions of elementary functions. And now let me show one example with using these expansions. For example, let's use number 5. So with natural logarithm. So how to work with these expansions? With this one. So for example, let's write an example. Natural logarithm 1 plus 3x squared, and expand these functions up to for example fourth order. So here we have the formula for natural logarithm 1 plus x. So this is same with this one, natural logarithm. If you want to put here minus, so we can find for minus also here, and let's write minus. So more difficult than this one. So now, but if it is minus, we can write like natural logarithm 1 plus minus 3x squared. So instead of our x, now we have minus 3x squared. And expand to Maclaurin expansions. So in this case, just use the formula. So x minus x squared over 2 plus x cubed over 3 factorial 3 plus etc. Yeah. So now we have instead of x minus 3x squared. So minus 3x squared minus. So this one is squared. 3x minus 3x squared is squared over 2 plus minus 3x squared cubed over 3. Yes. So if an example asked right up to the x fourth, it means the greatest one should be x fourth. So, but in our case, these two ones are enough, because here we have x4, and the next one is bigger than x4. If asked the x, for example, tens, we can take this one also, but in our case we cannot take it, the last one. So it is just we have minus 3x squared and plus etc. here, of course, because it's infinite. So minus 3x squared, and it should be plus, but in the middle we have minus 9x4 over 2. This is the expansion of our function up to the term containing x fourth degree. So using this elementary expansion of elementary functions, we can find easily for other ones. This is just basic ones for you. And now let's find for cosine 5x over 2. For this function, expand to Maclaurin's expansion. Okay, so here again we will use for cosine x the expansion of cosine x. Here it is cosine x, it was 1 minus x squared over 2 factorial even ones. Yes, x4 over 4 factorial minus x6 over 6 factorial, etc. So in general it is minus 1 the power of n x 2n over 2n factorial and plus small o x 2n plus 1. So now let's use this expansion and rewrite for cosine 5x. So cosine 5x over 2, cosine 5x over 2, it is 1 minus, so here instead of x just 5x over 2 we need to put 5x over 2 squared over 2 factorial times so it is x squared, here squared we have, yeah, and the next one is x fourth degree, it is plus 5x over 2 fourth degree over 4 factorial, etc. minus 1 the power of n, so 5x over 2 2n's power over 2n factorial plus small o x 2n plus 1. And now if you open our brackets we have here 1 minus 25x squared over 4, yes, because it is 2 squared, it will be so here 4 times 2, one more in the denominator we have 2 factorial, it is 2, plus here we have 5 fourth degree, it is 625 x fourth power over 2 fourths, it is 16 times 4 factorial, so 4 factorial it is 24, and plus etc. here plus minus 1 the power of n, so we can write just with, we can rewrite this one, 5x over 2 2n's power over 2n factorial plus small o x 2n plus 1. So this is we can simplify this expression, just multiply, and I think it's enough. So this is for cosine 5x over 2. And now for the next function, let's try to write for y. So the f of x is the function of so here f of x, it is cubic root of 8 plus x squared for this function. So now we can use here for 1 plus x m's power, 1 plus x m's power. Let's recall it is 1 plus mx plus m minus 1 2 factorial x squared plus etc. So now let's use this one, and right, but in our case it is 8 plus x squared, so it is f of x here 8 plus x squared degree of 1 over 3. 1 over 3. So in this case m is not integer number. So we need to rewrite this expression as 1 plus x. So we can take out this 8 out of our cubic root, and here we have just 8, 1 plus x squared over 8, and all of them in 1/3 power, or just 2, yes, times 1 plus x squared over 8, the power of 1 over 3. And now we can use our expansion Maclaurin expansion, and here we have f of x is our function now has the following expansion. So 1, we have here 2 before the brackets and 2 bracket, and this one now. So our x now x squared over 8. So 1, the first term is 1, plus mx. M is 1 over 3 in our case. And x is x squared over 8. Mx, so it is 1 over 3 times x squared over 8. And plus m minus 1. So it is 1 over 3 times 1 over 3 minus 1. 1 over 3 minus 1 over 2 factorial times x squared, or x fourths in our case, or 64. X fourths times over 64. And the general one is plus, etc. m minus 1, so 1 over 3 minus 1, etc. So 1 over 3, if we want to write for n's power, it will be 1 over 3 minus n plus 1 over n factorial, and x the power of n. So x square over 8 the power of n plus small o x to n now, because the here we have x to n, so the least one will be 2n. So this is Maclaurin expansion for our function. You can simplify this expression and close the brackets. So and get the final answer here. And now let's write Maclaurin expansion for the function arcsine x up to third order. Firstly, we need again find the first derivative of this function. It is 1 over square root of 1 minus x squared. And now find the value in this derivative. So it is 1 over 1 minus 0 in the square root, so it is 1. So firstly find f0, of course, also. So arcsine 0, it is 0. And now f second order derivative, it is 1 over 1 minus x squared. So now the derivative of this one is 1 over 2 1 minus x squared, and derivative of 1 minus x squared, it is minus 2x, and the minus, so here the first just this one, it will be plus, because here 0 minus this one, so it is just 2x over, and this is squared, so it's just 1 minus x squared now. So we have 2 and 2 are cancelled, x over, so 1 minus x squared times 1 square root of 1 minus x squared, or x over 1 minus x squared, the order of the power of 3 over 2, because 1 plus 1 over 2. And now the next one, third one, so the derivative is 0 here, because 0 over 1 here. F third order derivative is, now it is the derivative of x, it is 1, so 1 minus x squared 3 over 2 minus the derivative of this one, 3 over 2, 1 minus x squared 1 over 2 times 2x minus 2x, so here it will be plus 2x. Now over the denominator is 1 minus x squared and the power of, so it is cubed now, it's cubed. Okay, so f third one of 0, it is now it is just 1 here, here is 0, just 1. So we have 1 here, and now what we get, f3 is in the point of 0, it is 1, f0 is 0, f prime 0 it's 1. So just put now to the Maclaurin's expansion. So and then get the answer here. And so it is f of arcsine x, it is f0 plus x times f prime 0 plus x, so x squared over 2 factorial times f second prime 0, and the next one is f, so x cubed. Here we have x cubed up to third order. We need to expand this function. 3 factorial f 3 third order derivative 0. So now put just values. So f0 it's 0, f1 f prime of 0 is 1, so it will be x. This is also 0, you can see, and the third one is 1 also, so it is plus x cubed over 3 factorial, this is 6, plus small o x cubed, we can write here also small o x cubed. So this is expansion of arcsine x up to third order term. And it was the last example for today. So I think it's not so hard to understand the Taylor's and Maclaurin's expansion. The main idea is just remember the formula, the expansions of Taylor's and Maclaurin, and try to correctly use for the function. And also you have the expansions of elementary functions, and using these ones you can find easily other functions connected with these functions. Thank you for attention.